Now that we've started putting atoms together, it's worth revisiting what holds them together, specifically chemical bonds. What we're going to do here is review some of the concepts involved in bonding, including what makes a bond, what is an orbital, and how can we use orbital theory to understand how molecules are assembled and how they are shaped in 3 dimensions. So let's start with a little reminder about atomic orbitals. An electron in an atom can behave like a wave or a particle, but for our purposes, it's mostly useful to talk about the wave-like behavior of an electrons. The energy of an atom, which is a proton and an electron in some geometrical arrangement, is described by what's known as a wave equation. This is a mathematical formula which can solve for the wave-like properties of an electron. Solving the wave equation gives a series of solutions called wave functions, which are usually given the Greek symbol psi, psi1, psi2, psi3, and so on. The square of this wave function, or psi squared, indicates the probability of finding an electron in a particular location in space. Now, we're not going to dive too deeply into quantum mechanics here, but what we need to know is that an electron in an atom is a wave. There is an equation that describes the energy of a particular arrangement of a proton and an electron. This is known as a wave function, and the square of that indicates the probability of finding an electron somewhere in space. This probability, psi squared, is a function based on position and can therefore describe the shape of a 3-dimensional object, and that's what we know of as an orbital. The takeaway point here is that an orbital is some region of space with some size and shape inside which we have a probability of finding a given electron. In organic chemistry, we're mostly going to deal with s orbitals and p orbitals, although we will occasionally see species that involve their d orbitals, though we probably won't discuss them in depth. Just as a reminder about the shapes of these things, s orbitals are spheres, which I'm going to show as a circle here. If we could, we can imply the 3-dimensional geometry by adding a set of Cartesian axes here to show that this is actually a sphere in 3 dimensions. P orbitals I'm going to describe as peanuts. As you might remember from general chemistry, there are 3 p orbitals, a px, a py, and a pz. They all have the same shape with 2 equivalently sized lobes aligned along one of our axes. So the px orbital is aligned along the x-axis, the py orbital is aligned along the y-axis, and the pz orbital is aligned along the z-axis. Remember here that the pz orbital should be pointing straight out at us, but since we need to draw it on a 2-dimensional sheet here, we have to make some artistic sacrifices in the interest of being able to see our orbital in a way that makes sense. One idea we often touch on in general chemistry that will be more important for organic chemistry is the idea of the phase of the wave of an electron within an orbital. All waves have phase. For example, if I take a look at this sine wave here, there are points where I have positive amplitude that's above the axis. We would say that those regions of the wave have a positive phase. There are regions where the amplitude of the wave has a negative phase. Those are below the axis. And any place where the wave goes from a positive to a negative phase, crosses that axis, that's called a node. At a node, a wave has 0 amplitude. This is important for organic chemistry because if we're looking at a wave function, the square of psi squared, a probability density, anywhere where there's a node represents a place in space where the electron has 0 probability of existing. The rest of the issues of phase are going to come in when we're mixing waves together. You might remember from high school physics classes talking about constructive and destructive interference, and that has to do with if we're combining waves in phase, positive to positive and negative to negative, or out of phase, where the positive and the negative parts of the wave overlap. Let's look at a specific example of what I mean. Here's a p orbital. One thing that you should remember from general chemistry is that a p orbital does not actually come in contact with the nucleus of the atom. That's why we have 2 lobes with that little neck in the middle. Mathematically, this is because there is a node at the nucleus of a p orbital. And since the amplitude of our wave is 0 at the nucleus, that means the probability of finding an electron there is 0. One consequence is that anytime a wave passes through a node, the phase of the wave has to change. So that means that each lobe has a different phase associated with this mathematical description of the wave-like properties of an electron. In organic chemistry, what we're usually going to do is indicate phase with color. So we're going to color one of these lobes red to indicate, say, a positive phase, and we're going to color the other lobe blue to indicate, for instance, a negative phase. The colors don't actually matter, and it's important to note that the phase that we're talking about here, positive and negative, doesn't indicate something about the charge of an electron. It's a mathematical property based on the wave-like nature of the electron. The important part is that the two lobes have this opposite physical property that we call phase. There's not actually a great physical analogy for what's going on here. Okay, so let's get to the next step now and use these things to make orbitals. What we're going to be talking about now is valence bond theory, and we're going to bring our orbital description of atoms into explaining why bonds form. So in the Lewis model, bonds form because we have two atoms, say these two hydrogens with unpaired electrons. If those electrons are shared between the two atoms, we form a bond. The Lewis model mostly describes bonding as being a consequence of wanting to get to some stable state where we filled the valence shell of each atom, but that's an incomplete description of what's actually happening. A better model is the valence bond model using molecular orbitals. So here we're saying that we have two hydrogen atoms. Each contains a single s orbital, and when we bring those orbitals close to each other, the orbitals overlap, forming what we know of as a bond. The reason why this is useful is it matches how we've described bonds in general chemistry as a consequence of electrostatic attraction. Since we're stuffing negatively charged electrons in between two positively charged protons in the nucleus of the atom, we've reached a state where we've come to some sort of optimal arrangement in terms of the electrostatic interactions between the atoms. Now, though, we can actually use orbital phase to put together sort of a more complete description of what happens when two atoms start to overlap. One important consequence of molecular orbital theory is that there's two possible solutions for interactions between two orbitals. We can have an in-phase combination and an out-of-phase combination. So for instance, if I was starting here with two individual hydrogen atoms very far apart, there's two possible solutions for when I bring these things closer together. I could draw one picture where I've placed both of the atoms in phase with each other. Now this is going to correspond with what we think about as a bond with electrons being shared between two atoms. Remember from physics that if we have two waves combining with the same phase, they constructively interfere and reinforce. So that means that my probability density, the chance of finding an electron, is increased between the two atoms, which is how we generally describe what a bond is. If we look at the other solution where I combine these two things out of phase, the two orbitals, the waves are going to cancel each other out where they start to overlap between them. This is destructive interference, and this corresponds with a higher energy state where the electrons are actually forbidden from existing between the two atoms. If we actually go the next step and draw what this would look like, we'd combine the two orbitals on the bottom to get a new molecular orbital that looks like this. On the top, the two orbitals would cancel out where they touch, leaving us with a new node and a picture that looks like that. The way that we're going to name these molecular orbitals is based on the symmetry of the picture that we've drawn. These are both sigma orbitals since they both have cylindrical symmetry. If we describe a p orbital as shaped like a peanut, you can think about a sigma orbital as shaped like a sausage. If you rotate it along the axis, it's not going to change no matter what angle you look at it from. On the bottom, we're going to call this a sigma bonding orbital because we've combined our waves in phase to increase the electron density between the two atoms. So we'll label that sigma. On top, this is going to be called an anti-bonding orbital because it looks like the opposite of what a bond would look like. We're going to label that one sigma star. It gets the same designation because it has the same type of symmetry. The star, the asterisk, indicates that this is an anti-bonding orbital. In organic chemistry, we are mostly going to be dealing with the bonding orbitals of molecules. We will only need to look at the pictures of the anti-bonding orbitals when we deal with reactions. So what happens if we have p orbitals? Well, p orbitals combine to make pi bonds, which we'll mostly see in molecules with multiple bonds. We can draw the same sort of picture and do the same type of analysis. Here are my two p orbitals separately. I can bring them together, and there's two possible ways to combine them. I can combine them out of phase to make a high-energy antibonding orbital, or I can combine them in phase to make a low-energy bonding orbital. Now, the way these orbitals look will be very different from the sigma orbitals. Here's what my antibonding orbital looks like. We will give that the label pi star. This is a pi orbital, and it's the antibonding type. If I combine them in phase, I get a pi bonding orbital, which looks like this. And again, we'll mostly need to deal with pi orbitals when we're having to make or break multiple bonds. We'll come back to this when we talk about the structure and the three-dimensional geometry of some more complex molecules a little bit later. So now that we've talked about the basics of molecular orbital theory, we're going to revisit hybridization states and use that as a way to describe and predict the three-dimensional geometry of more complex molecules.